So last week our main conclusion was that we were actually able to build one circuit that was going to evaluate any other circuit that we could give to it. So the motivation to this was that we knew that we could compute any finite function we wanted to with circuits. So if we were going to need to build just one particular circuit, we needed to pick what function that was going to be in advance. So we might as well pick one that sort of doesn't limit our options. So we picked that eval circuit, where the idea of the eval circuit was that we could give it any program and it would tell us what that program would output on a particular input. So now I personally think that this is actually really cool that we can have a hardware-based model of computing like our circuits that can simulate the behavior of like a software or programming language model of computing like the straight line programs, where we took a straight line program, we came up with a representation, and then we were able to put it on an actual Boolean circuit in order to figure out how it would answer. And I think this is really cool because this is actually how computer science works. That we have these hardware devices, our computers, these physical machines, and we as humans, the way that we get those machines to do different things is we write software to go on them. So we have software that's really nice for humans, we have hardware that we can actually implement in some physical form factor using electricity and the like, and because the hardware has this ability to simulate what the software does that we're giving to it, that's what actually allows us to do computing in sort of a convenient way. So right now we've only done this with circuits, which is a pretty limited model of computing, but we're going to see this same idea pop up again when we talk about more complicated models of computing that are going to be able to do more powerful things. So this is just a really profound idea, this idea that you have simulation of software using hardware that we need in order for computing to have developed in the way that we currently pursue it. So now, once we have these evaluation circuits, this sort of brings up some other questions that we might want to consider. Since circuits can only do finite functions, we have to pick the size of the circuit in advance that we wanted eval to do. So we couldn't make an eval circuit that would work for any program that we might pick. We instead had to make an eval circuit that would work for programs up to a certain size, because we needed that to be a finite function. So if we were to sit down and decide, like, all right, I want to build this eval circuit, what size should I make it? So we might want to ask this question, like, how expensive are various functions? If I have certain functions in mind that I would like to compute, I need to pick how big should my eval circuit be in order to enable me to actually simulate that function. Or I might want to say, if I were to make my eval circuit this size, what things am I going to be able to do? What things am I not going to be able to do? So it's going to help me inform this decision about what is the right size circuit for me to be able to implement here. So what we're going to be talking about today is we're going to be talking about a way that we can measure how expensive different functions are. That's really going to allow us to formally study this notion that we've talked about for weeks now, that some functions are going to be more expensive than others, and to the point of saying how expensive can different functions get. So maybe what we're going to want to be able to answer is this question of, like, if I wanted to be able to evaluate a program for any function that was going to map n bits of input to 1 bit of output, how big should that circuit need to be? So we have these various questions that we're going to be able to answer using some of the tools that we developed this week. So what we're going to be talking about this week is a notion called complexity and complexity classes. We're going to introduce that in the next video. And we're going to be talking about asymptotic notation, which is the most popular tool we use for categorizing things based on the resources that they're going to use.